Today we are going to see the chemistry of lanthanide. As we know, A block elements have two series, and 4F series is known as lanthanide, and second 5F series is known as actinide. So we are going to see that there are total 14 elements in the lanthanide series. So first series of A block is the lanthanide, and here we are going to see the position of lanthanide in the periodic table. After that, the electronic configuration, and then atomic and ionic radii, and some properties of these lanthanide elements. So the topic is a chemistry of lanthanide, and lanthanide A block element have two series. First series 4F series is known as lanthanide, and this lanthanide is also known as that is the rare earth elements, and sometimes it is also known as inner transition element. And here the element of the lanthanides, total elements are 14, and starting from lanthanum is the first element, and from cerium to lutetium are the 14 elements in the series. The element in which the last electron enter the F orbital of their atoms are called A block element. In this element, last electron is added to the anti-penultimate energy level, that is n-2 F shell. These elements are also known as inner transition element. These elements consist of series consist of two series of the element placed at the bottom of the periodic table. These two series are generated by the filling of electron in the 4F or 5F orbital. The first series involves filling of 4F orbital and follow the lanthanum, and this is also called lanthanide series, and the element present in the series are called lanthanides. There are 14 elements in the series, starting from cerium atomic number 58 and ending with lutetium atomic number 71. All these elements have closely similar properties and therefore are considered together. The reason for their similar property is that the 4F electrons in which the electrons are added are embedded in the inner shell, while 5D and 6S electrons which have similar configurations are exposed more to the surrounding. Because of their similar physical properties, their separation and identification is a very difficult task, and therefore first stage in their separation is to get them as an oxide. However, occurrence of oxide of lanthanide are very rare, and therefore these elements are also known as rare earth element. And so these are the lanthanide series starting from atomic number 58 to 71, and also these elements occur rarely and therefore also known as rare earth element. And in the next slide we are going to see what is the position of lanthanide in the periodic table. So here it is shown the position. As we know, this is S block, P block, D block in the middle, and F block are shown separately at the bottom of the periodic table. This is the 4F series. Two series are there in a block, 4F series and 5F series. So 4F series is known as lanthanide, 5F series is known as actinides. So this is the cerium to lutetium. These are the 14 elements of lanthanide, and the second series is known as actinide series. So we have to see the chemistry of these lanthanide elements, and as we know their position, all the elements have similar physical and chemical properties, and therefore they are shown. Here is the lanthanum. Therefore these elements are also known inner transition element. So all these 14 elements are here. After lanthanum, here is now 57 and 58 to 71. Here is the position. All the elements are having similar property, therefore they are shown the same position here. The position is here, and but there is no space, and therefore they are shown separately at the bottom of the periodic table. And so they are known as F block element are known as inner transition because they are present to the inner to the transition element. And therefore these are the 15 element from lanthanum to lutetium from atom number 57 to 71 are called lanthanide, or also known as rare earth, as shown in the periodic table. The element involves filling of 4f orbital. To understand the position of these elements in the periodic table, we start with the electronic configuration of xenon. And xenon have atom number 54. Xenon has the electronic configuration, as we know, atom number 54, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2 and 5p6. And further addition of electron take place in 6s orbital, giving an alkali metal cesium and a rare earth element barium. So at barium, all three subshells 6s, 5d and 4d have very similar energy. In lanthanum, the electron enter in 5d orbital, and therefore its configuration is xenon 4f0, 5d1 and 6s2. As we move a step further, the 4f subshell become definitely more stable as compared to the 5d subshell, and therefore next electron in cesium enter the 4f subshell. So the configuration of cerium Ce become atom number is 58 and xenon 4f2, 5d0, 6s2. The 4f subshell continue till filling of 4f subshell continue till we reach the terbium Yb, having the configuration xenon 4f14, 5d0, 6s2. Now when 6s and 4f orbital are completely filled, the next electron enter the 5d orbital. And so in lutetium, atom number 71 has the electronic configuration xenon 4f14, 5d1, 6s2. In this case, F have 14 electron, S have 2 electron and 5d1. These elements can be given the general electronic configuration xenon, atom number 54, then 4f 0 to 14, 5d 0 to 1 and 6s2. And therefore, because of the similarity in the electronic configuration, they show similar chemical properties and are grouped at one position in the periodic table. So, but in the transition element, there is, after lanthanum, there is no any space. Therefore, they are shown separately at the bottom of the periodic table as a F block and F block, and these two are lanthanide series and actinide series. So, we are going to see the properties of these lanthanide series. And our first property is, after the position, we are going to see is the electronic configuration of lanthanide. So there are 14 elements after lanthanum, and these 14 elements are shown here. This is lanthanum is the first member, and start from cerium to lutetium. So the elements are 14 elements are cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, terbium and lutetium. These are the symbols, and atom number 57, and from 58 to 71 14 elements are there. And their electronic configuration are being shown here. Xenon have 54 atom number. This is the general electronic configuration, and xenon have 54, then 57. So what is then 3 electrons? So 4f0, 5d1, 6s2. Next incoming electron goes to the 4f, and therefore the xenon cerium have electronic configuration 4f2, 5d0, 6s2. So 4f orbital filled progressively here in this way up to 14. After completing, then electron will go to the 5d orbital, and so this is the electronic configuration shown here. And in this case of electronic configuration of lanthanide, lanthanum follow the barium, and barium has electronic configuration xenon 6s2. In lanthanum it is xenon 5d1 and 6s2. This shows that all the lanthanide have inner core of xenon, but electronic configuration of 4f block element is still not very clear. In xenon, 4f and 5d subshell are empty, and therefore after lanthanum, last electron can be added to the 4f or 5d. According to the Bohr-Bury scheme, 5d cannot get more than one electron until 4th main energy level is filled to its full capacity. The electronic configuration of valence shell in that case can be 4fx 5d1 6s2, or we can also write 4f x plus 1 5d0 6s2. The configuration 4fx 5d1 6s3 agree with the tetra or tervalent nature of these elements, but does not agree with the spectroscopic data. Spectroscopic study shows that up to lanthanum 4F has higher energy than 5D, but as soon as the atomic number increase by 1, like cerium 58, it falls below 5D. Therefore, the successive last electron prefer 4F subshell, and this support 4F subshell, and therefore this support the 4F x plus 1 5D0 6s2 electronic configuration. So in lanthanum, gadolinium and deuterium 5D receive 1 electron to maintain the spherical symmetry of F orbital, and the electronic configuration of these elements are already shown in the table. So this is the reason that 4F subshell accept electron instead of 5D, and only in the 3 element lanthanum and this gadolinium and the last deuterium have 5D have 1 electron. So 6s orbital is completely filled, and incoming electron goes to the 4F. After completing 6s and 4F, then electron will go to the 5D. So this is the reason that, and this is the electronic configuration in the table. And next property that we are going to see, the variable oxidation state. As we know, some elements are there of the transition element also show variable oxidation state, and these lanthanide and actinide series also show some variable oxidation state. And in this case, table shows that here the oxidation state shown in the bracket are less stable, and common oxidation state shown by all the element is a +3. So +3 is the common oxidation state shown by all the element, and some elements show +2 oxidation state, and some are showing +4 oxidation state. So these are the variable oxidation state. As we know, oxidation state is a tendency of an element to lose electron or to gain electron. When they lose electron, they have a positive oxidation state. When they gain electron, they have a negative. So all these elements show tendency to lose electron and have positive oxidation state. So oxidation state of lanthanide is shown in here in this slide, and lanthanide exhibit a remarkable oxidation state of +3 in most of their ionic compound. Oxidation state of +2 and +4 exhibited by some member of the lanthanide series. The oxidation state of this series also shows that from the table it is observed that all the lanthanide commonly show +3 oxidation state. Lanthanum, gadolinium, deuterium show only +3 oxidation state. To acquire 4F0, 4F7, 4F14 state element, close to these elements show variable oxidation state. In addition to the +3, some element cerium, praseodymium, thorium, dysprosium also show +4 oxidation state, whereas samarium, europium, thulium, terbium also show +2 oxidation state. So some common oxidation state shown by these elements is +3, and some elements show +2 and +4 oxidation state. So in short, we can say that lanthanide show variable oxidation state. So this is the important property of these lanthanide series. And next property is atomic and ionic radii of the lanthanide series. And here table shows the values of atomic and ionic radii. So in case of atomic radii, these are the elements. These are the atomic number 57 to 71. And here atomic radii in angstrom is shown here. Atomic radii slowly decreases here with the increase of atomic number. As the atomic number increases, this is the slowly decrease of atomic radii of these elements. And as compared to this is +2 and +4, but +3 common shown by oxidation state shown by all the elements. And here this is very clear that there is a decrease in ionic radii, very clear as compared to atomic radii. So in case of atomic and ionic radii, and from the table it is seen that atomic and ionic radii of all the lanthanide decreases gradually with the increase in atomic number. However, the variation in atomic radii between lanthanum to deuterium is less regular than in ionic radii, and therefore decrease in ionic radii from lanthanum to deuterium is only very slight, and which point out that variation is quite small. This small decrease in atomic size and ionic radii of lanthanide element with the increase in atomic number is known as lanthanide contraction. So this is the lanthanide contraction, and it is clear from this table that atomic and ionic radii decreases from lanthanum to deuterium, This anomalous decrease in the size of atom or ion is called lanthanide contraction, and decrease in the size of ion is more regular as compared to the atom. And so now in the next slide we are going to see, this is the figure which shows for atomic covalent radii and the ionic covalent radii. This shows that those two elements have exceptionally high atomic and ionic radii. It is due to the spherical symmetry of electron in Fourier subshell and difference in metallic bonding. Except europium and terbium, all other lanthanides contribute 3 electrons for bonding. Europium and terbium contribute only 2, having half filled and completely filled Fourier subshell respectively. And therefore, from this graph, it is clear that curve can be divided into 2 equal parts at gadolinium. Right half of the series, that is terbium to lutetium, is a repetition of left half, that is from cerium to gadolinium. In the formation of lanthanides metal ion, all the lanthanides give off 3 electrons. The electrons are lost from 6s and 5d or 4m. Due to continuous increase in the effective nuclear charge, the ionic radius for tripositive ion decreases from lanthanum 3+ to lutetium 3+. And this table shows that, and this figure also shows that there is a discontinuity at the gadolinium 3+. This discontinuity and repetition of properties from gadolinium onward is known as gadolinium break. So here, this is the figure shows, this is the atomic radii shown by the solid line, dash dash is shown by the covalent radii. So these are the two, and there is at the gadolinium there are the 2 breaks. So here, this is the gadolinium break, which is known as gadolinium break, and shows the higher value of the 2 elements, exceptional these. And so in short, we say that these elements show slight decrease in the atomic and ionic radii with the increase of atomic number. This decrease in atomic size or atomic radii is known as lanthanide contraction. So today we have seen the chemistry of lanthanide, and in the lanthanide studies, this lanthanide is also known as rare earth element, also known as F block element. So 4F series is known as lanthanide, and in this case we have seen 4 important properties. One is the position of lanthanide in the periodic table, electronic configuration of lanthanide, variable oxidation state, and 4th is the atomic and ionic radii. So as we have seen, there is a decrease, slight decrease in the atomic and ionic radii from lanthanum to lutetium. This decrease is with the increase of atom number is known as the lanthanide contraction. So today we stop here, and in the next part we are going to see what is lanthanide contraction, what is consequences of lanthanide contraction, and separation of lanthanide element and different methods.